Let's tackle this AP Calculus free response question that includes concepts from units 2, 3, and 5. Consider the curve given by the equation 2 times the quantity x minus y equals 3 plus cosine y. For all points on the curve, 2/3 is less than or equal to dy over dx is less than or equal to 2. So we have this implicitly defined function. It's got x and y mixed together in the expression. And we also know that the derivative is between 2/3 and 2 for all points on the curve. And we're going to answer 4 questions related to this situation. And we'll tackle each one on a different slide. So we'll change slides and start with part A. So in part A, they simply want us to show that the derivative, dy over dx, is equal to 2 over 2 minus sine y. And so we're going to have to do implicit differentiation. So let's start that over here. I'm going to rewrite the expression. 2 times quantity x minus y equals 3 plus cosine y. Let's distribute. And I like to distribute. It just makes it easier for me when I'm working with derivatives. You could do it without that, but... Okay, so I've distributed, so the expression is a little easier to work with, and now I'm going to start the implicit differentiation. The derivative of 2x is 2. The derivative of 2y is 2 times dy over dx. The derivative of 3 is 0, and the derivative of cosine y is negative sine of y times dy over dx. Once we do the derivative, our goal is to collect the dy over dx terms, isolate it, and solve. So I'm going to rearrange things a little. It looks like if I bring if I do plus 2 dy over dx on both sides and then flip it around, so I'm going to add it here and add it here. If I do that and then pull the old switcheroo, I think you'll agree that I get 2 dy over dx minus sine y dy over dx equals 2, right? Just to show you what happened here. These canceled, so here's my 2. And here on this side, these are like terms, so what I'm going to do is collect them, but I just wanted you to agree that I did that okay. Notice we have a dy over dx here, so I'm going to factor it out. Oops, not equals. Not yet. It's going to equal something, but right now we've just factored out. This is a 2 minus sine y, and we knew that's what we were hoping to get, so that's good. Now I'm just going to divide on both sides by this expression, 2 minus sine y and 2 minus sine y, and we've got it. Okay, I'll just rewrite it over here on the side, but we have shown that the derivative dy over dx does equal 2 over 2 minus sine y. Now keep in mind, this is still implicitly defined, right? There's no x value in or x term in this expression, but there is a y term. So the derivative is defined in terms of the original function. But we've accomplished what they asked us to do. So far, so good. Okay, check off the implicit differentiation, and we'll move on to part B on the next slide. In part B, it says, for negative pi over 2 is less than y is less than pi over 2, there is a point P on the curve through which the line tangent to the curve has a slope of 1. Find the coordinates of P. So we're trying to find P. We know that the y values are between negative pi over 2 and pi over 2, and we know that there is a tangent line with a slope of 1. So I'm going to start with that slope of 1. We just figured out that the derivative was 2. Let's not use yellow. That may not be the best color to use while we're doing this. It's good for highlighting, but not necessarily good for writing math. 2 over 2 minus sine y is the derivative, and we know that at this point P, the derivative is 1, right? The slope is 1, slope of the tangent. And so I can solve for y here, right? Multiply the 2 minus sine y over here. This tells me that negative sine y equals 0. The sine of y is 0, and therefore y equals 0. Okay, that's the y coordinate. To get the x coordinate, I have to plug y into the original equation. And I'm going to kind of move over here. I sort of ran out of room. Let's see if we can squeeze in another line right here. I'm going to plug 0 in for y and solve for x. So that gives me 2 times x minus 0, or 2x, equals 3 plus cosine of 0. And let's see, this is just 2x, and 3 plus cosine 0 is 1, so this is 3 plus 1. So this is x equals 2. 2x equals 4, you divide by 2, you get 2. So the coordinates of P are 2, 0, and we are done. All right, not bad. Coordinates of P are 2, 0. Just double checking to make sure I didn't miss anything. We've answered the question. Slope is 1. All right, we will move on to the next slide and attack part C. Part C says, determine the concavity of the curve at points for which negative pi over 2 is less than or equal to y is less than or equal to pi over 2. And of course, we're going to give the reason for our answer. Determine the concavity of the curve where y is in this range. Remember, we investigate concavity by looking at the second derivative. And since we know the first derivative, we can just do the derivative again and then examine the second derivative. So the first derivative is 2 minus sine of y, 2 over 2 minus sine of y. Let's rewrite that as a power just so I don't have to mess with the quotient rule. I know that's cheesy, but in this case, I think it's appropriate. Okay, so I'm going to do the second derivative with a notation for that. The Leibniz notation is d2y over dx2, d squared y over dx squared. We'll do a power rule and then a chain rule. So this is going to be negative 2 times 2 minus sine y to the negative 2 times the derivative of 2 minus sine y, which is negative cosine y. I'm running out of room here, so forgive me, but I'm going to put negative cosine y right here. And then times the derivative of y, which is dy over dx. And remember, we already have an expression for dy over dx, so that's going to come into play. Okay, right here. Let me clean this up a little bit. I wish I would have started this over on the side. So I'm going to, like it or not, I'm going to pick up over here. And let's see if we can clean this up. Okay, so the 2 minus 2 sine y to the negative 2, that's going to end up in the denominator of a fraction. I've got a negative 2 times a negative cosine y. That's the numerator, so that's 2 cosine y. I've got, what did I say this was, squared? And then remember, we're multiplying by the derivative, which is 2 over 2 minus sine y. Okay, so finishing this second derivative off so we can examine it, I'm going to have in the numerator 4 cosine y, and in the denominator, I'm going to have 2 minus sine y to the third power. Okay, so we need to examine the sign of this second derivative. So I want to just point out a couple things to you. First of all, when y is between negative pi over 2 and pi over 2, actually it's not equal, it's just strictly less than. Cosine y is positive. Cosine's positive in the first and fourth quadrant. How do I want to write that? I'm just going to put is positive. So that means the numerator is going to be positive on that. And the sign of y is going to change signs, but sign of y is going to be between negative 1 and positive 1. Right? Those are the extremes of that function. So that means this 2 minus sine of y is always going to be positive. And when you cube a positive, you still get a positive. So we know that, and I'm going to wrap this thing up, we know that d2y over dx2, d squared y over dx, the squared, the second derivative, not equals, is positive on this interval. Therefore, the curve is concave up. Am I going to be able to fit it in? Nope. I'm just going to put concave up. And we'll just highlight it and we'll pretend like that's a good answer. I'd prefer writing that out as more of a sentence. Since the second derivative is greater than 0 on the interval, the curve is concave up on that interval. But you can see that we did the math here, and hopefully you get the gist of the strategy. You are forced to examine the sign of this expression on the interval, the sign, the SIGN, and we've discovered that it's positive. Okay, that wraps up part C, and now we just have to attack part D and we'll be done. Part D, let y equal f of x be a function defined implicitly by 2 times the quantity x minus y equals 3 plus cosine y. That is continuous on the closed interval 2, 2.1, and differentiable on the open interval 2, 2.1. Use the mean value theorem on the interval 2, 2.1 to show that 1 over 15 is less than or equal to f of 2.1 minus f of 2 is less than or equal to 1/5. So there's a lot going on here. Essentially what we're saying is that we actually have a function f of x. It's defined by that expression that we worked with earlier, the equation that we worked with earlier, which is this implicit equation here. And we're going to use the mean value theorem, and we want to end up here. Let's start by reminding ourselves the statement of mean value theorem. Our function f fulfills the hypothesis. Okay, so f of x does meet the hypothesis for the mean value theorem. It's closed. It's continuous on the closed interval and differentiable on the open interval. That means that there exists a c in that interval such that f prime of c equals f of 2.1 minus f of 2 over 2.1 minus 2 for some c in 2 comma 2.1. Now we don't care what C is right now. We just know that that's the setup for the mean value theorem. All right, now remember back to the original statement of the problem. They told us that the derivative was trapped between 2/3, and I'm writing f prime of x instead of dy over dx because remember, y equals f of x, so I can write this and it's still true. That derivative is trapped between 2/3 and 2. And we just said that there's some c in the interval, some x value in the interval, that the derivative equals this expression. So I'm going to take that expression and stick it right here where f prime of x is. So I can say 2/3 is less than or equal to f of 2.1 minus f of 2 over 2.1 minus 2. That's less than or equal to 2. I can do that because all of the derivatives for this function are between 2/3 and 2, so certainly the derivatives on this interval are there. And then basically what I need to do is I want to end up with just f of 2.1 minus f of 2 in the middle of this compound inequality. So I'm going to multiply the whole doggone thing by, let's see, the denominator here, which do you agree this is just 0.1? So let's multiply by 1/10 or 0.1. And when we do that, I think we'll have what we want. 1/10 times 2/3, I'm going to cross out the 2 and the 10. That's just 1/15, so that's good news. The denominator is gone, so that's good news. We get the expression we wanted, f of 2.1 minus f of 2. And then as long as 2 times 1/10 is 1/5, which it is, we made it. And we've achieved what they were asking us to achieve, which was to show that the f of 2.1 minus f of 2 was trapped between 1/15 and 1/5. So we did it. It's right here. All right, that's great news. Get my highlighter going here, and we should be all set. Okay, so lots going on in this problem. We attacked all 4 parts, and hopefully that helps you as you're working through this problem. If you need anything else, you know where to find me. Good luck. Take care.